You know, when we see images of NASA's Artemis program, our minds immediately go to the massive rockets, the cool spacecraft, the astronauts, right? But what if I told you to look past all that engineering? Because what Artemis really is one of the toughest, highest stakes final exams for chemistry you could ever imagine.
So let's get right into it. Every single phase of this mission, from the pure violence of the launch to just keeping an astronaut alive in the silence of space, it all boils down to a fundamental chemical principle. And this isn't some problem set in a textbook. This is chemistry where one tiny miscalculation, well, there are no do-overs.
All right, first things first, getting off the planet. To break free from Earth's gravity, you need a mind-boggling amount of energy. But here's the catch. It can't just be a giant bomb. It has to be a perfectly choreographed, perfectly controlled release of chemical power. We're talking about controlled violence on a massive scale.
And at the absolute heart of that power is a concept we all know well: combustion, a good old redox reaction. Seriously, you can think of the Space Launch System rocket as the most powerful, most sophisticated Bunsen burner ever created. And the whole thing works because of one simple driving force. Electrons are desperate to move.
It sounds almost silly to put it that way, but it's the literal truth. Inside those RS-25 engines, you've got your liquid hydrogen fuel and your liquid oxygen oxidizer. The electrons in that hydrogen are just buzzing in this high-energy state, and they're practically begging to jump over to those super electronegative oxygen atoms. That massive, enthusiastic rush of electrons is what unleashes that incredible flood of energy.
And here it is, the core reaction. Looks pretty simple, doesn't it? Something you'd balance in a heartbeat. But this is where those stoichiometry classes become deadly serious. If that mass ratio between hydrogen and oxygen is off by even a tiny fraction, you don't just get a bad grade, you get a failed launch. In rocket science, there's no partial credit. It has to be perfect.
Okay, so that incredible chemical violence gets us off the ground. But the second the Orion spacecraft is in orbit, the mission completely changes. Chemistry's job flips from creating overwhelming power to maintaining this tiny, delicate, stable bubble of life in the middle of, well, nothing.
Now this part is just so brilliantly clever. The spacecraft gets its electricity from the exact same ingredients that launched it, hydrogen and oxygen. But instead of just letting them explode together, we turn to electrochemistry. A fuel cell basically tells those same eager electrons, hey, you can still get to the oxygen, but you have to take the long way around, through this circuit. Their journey becomes our electricity. It's the same reaction, just handled politely.
I love this idea, because while everything outside the spaceship is alien and extreme, the goal for the inside is for it to be utterly, completely boring. And a huge part of that is managing the very air they breathe. See, every time an astronaut exhales, they release CO2, which in a tiny sealed box is a poison. So how do you solve that? You guessed it, more classic chemistry.
This is straight out of Chem 101. The CO2 they breathe out dissolves in moisture and forms carbonic acid. Let that build up, and the crew is in serious trouble. So, the life support system uses these elegant chemical buffers, yep, just like the ones you'd use in a titration lab, to constantly neutralize that acid, keeps the pH stable, and ensure the air stays wonderfully, life-savingly, boringly normal. So we've made it. We're at the moon. Mission accomplished, right? Oh, not even close. The moon isn't a finish line. It's a whole new and arguably much harder set of chemical problems. It is a chemist's nightmare. Just look at that number for a second. That's not the high temperature. That's the temperature swing. We're talking about plunging into deep, cryogenic cold and then baking at temperatures well above boiling. For any material trying to exist there, that is just a brutal, relentless assault. And it's so much more than the temperature. You've got a hard vacuum trying to pull gases out of your materials, making them brittle. You have constant radiation that literally shreds the chemical bonds in polymers. And then there's the regolith, this ultra-fine, razor-sharp, electrostatically charged dust that gets into every crevice and acts like microscopic sandpaper. So how in the world do you build a spacesuit, or a tool, or a habitat that can actually survive all that? The answer is materials chemistry. This is where scientists go down to the molecular level, designing specialized alloys and ceramics and polymers. They're literally building survivability right into the material's DNA, creating specific bonds and crystal structures that can handle the unsurvivable. But just surviving isn't the real goal, is it? The dream is to thrive, to stay. And that brings us to this incredible concept, ISRU,
which is just a fancy way of saying living off the land. This is where analytical chemistry and geochemistry get their moment to shine. The idea is to stop dragging everything from Earth and start making what we need from what's already there.
So what are we looking for in all that moon dust? Well, finding water ice in those dark craters is obviously a massive prize. But here's the crazy part. The most abundant and valuable resource on the moon is oxygen. It's everywhere, but it's chemically locked up tight inside metal oxides. Think silicon dioxide, aluminum oxide. The grand chemical challenge is figuring out how to efficiently crack open those incredibly strong bonds to release pure oxygen we can breathe and use for rocket fuel.
So you see how it all weaves together, right? From the redox of the launch, to the electrochemistry on the spacecraft, to the material science on the surface. It's all one continuous chemical story. But there's one final test in this exam, and it's an absolute monster, coming home. That final plunge back to Earth, it's a terrifying thermochemistry problem. Hitting the atmosphere at those speeds creates unimaginable heat, and the solution is so counterintuitive. Instead of a shield that reflects the heat, we use one that embraces it. It's an ablative shield, designed to literally burn away. It uses all that thermal energy to drive endothermic reactions, sacrificing itself layer by layer and turning heat into a chemical change to keep the capsule safe.
So, for any of you who have ever been in a lecture hall wondering, when am I ever going to use this? Well, here's your answer. The success of Artemis rests on perfect stoichiometry, a deep understanding of reaction kinetics, the ability to think about chemistry and engineering as one big system, and even sustainability with closed-looped systems. This is your textbook brought to life on the grandest stage imaginable.
The Artemis program is this incredible laboratory forcing us to solve the moon's unique chemical puzzles, which leaves us with one final huge question to think about. As we look ahead to that next giant leap, what are the even harder, even more complex chemical questions we're going to have to answer to survive on Mars? Something to chew on. Thanks for diving in with me.